Assalamu alaikum students. Today's topic is going to be about Carnot engine. Carnot heat engine basically is a specific kind of engine in which the system, whatever you put into the system, that means the input, you get 100% as a output, as a useful work done. Such type of ideal, or we can say in other words, imaginary engine is known as Carnot engine. Let us read about it. A heat engine is a closed system that exchanges only heat and work with its surrounding and that operates in cycles. That means if this is a system, if we give heat to this system, it does two things basically. One is a useful work done, and some of the heat is being lost as heat loss, or you can say friction, or you can say heat sink. All cyclic engine driven or heat engine from the heat source and convert some of it into useful work, which is this one, and reject the remainder to heat sink, which is right over here. As a matter of fact, all engine possesses dissipative effect. That means they will give off some heat due to friction, due to grinding between the materials inside it. Hence, the efficiency of the heat engine is reduced considerably. In order to set an ultimate limit to the efficiency of the heat engine, a French military engineer by the name of Sadi Carnot in 1824 considered an hypothetical, that means imaginary, idealized heat engine which is free from all sorts of heat loss. That means there is no heat loss in this system, and friction, which is called Carnot heat engine. The efficiency of an actual engine is always less than the Carnot engine. So in actual engine there must be grinding between the different parts of the machine of the system, not in Carnot engine. That is why the Carnot engine, you'll get more work out of it as compared to the actual engine. But this Carnot engine is imaginary, it's hypothetical. Let us understand the construction of this simple engine. So a Carnot engine consists of a cylinder with a perfectly insulating wall and perfectly conducting base. So here's a cylinder and its walls over here are insulating. That means no heat can get into the cylinder and no heat can get out of the cylinder as well. Whereas it is perfectly conducting. That means the base of this engine is conducting. Even if you send a little amount of heat into it, it will gather up that as well. A perfectly insulated, weightless, frictionless piston in the cylinder. That means here's the piston and it is insulated. That means no heat can get out of here like this. And it is weightless. That means it has considerably no extra weight. And it is frictionless. That means no friction occurs over here as well. It moves like this. Now, if we have to understand the Carnot engine, we have to understand the Carnot cycle. A Carnot cycle or cycle of heat engine is completed with the property of a system have returned to its original state. That means wherever it started from, it goes back to its original point where it started from. The operating cycle of most of the efficient engine, which is Carnot engine, is called Carnot cycle. That means this type of cycle being used in a Carnot engine is known as Carnot cycle. It consists of four processes. Two, isothermal. Isothermal processes are those processes in which temperature remain constant. As the pressure and volume changes, the temperature will remain constant. Whereas the other two adiabatic processes are those processes in which basically there is no heat given or taken from the system, and whatever goes inside it basically gives off the heat or takes away the heat, which is a very fast system or fast process, whereas in the case of isothermal, it is a very slow process. Keeping that in mind, fast and slow, we move on to the procedure now. Isothermal expansion. Now, in this case, we have to consider a Carnot engine. Let working substance system be at pressure P1, volume V1, and temperature T1. So over here in the cylinder, or we can say system, the volume is V1, the pressure exerted by the piston is P1, and the temperature inside is T1. Let the gas cylinder be placed on a high temperature reservoir at temperature T1, and some amount of heat energy, which is plus Q1, is absorbed by the gas, keeping the temperature of the gas constant. Now, as you can see, very slowly it begins to increase. We are decreasing the pressure very slowly. So first it was over here. As you can see, it moves very slowly in the upward direction. Why is this so? Because the molecules inside it basically are colliding, but as they get more space, they will collide less. And the average kinetic energy inside this whole container will decrease because of the more space or more volume. In this case, the temperature inside the container should basically decrease. But to remain at a constant temperature, we get it's some heat. So it absorbs some heat. So that is why plus Q is written over here, keeping the temperature of the gas constant. And as you can see, the volume has increased, but the pressure has decreased. As you can see over here, it was over here, it moved from here till here. So this much volume has been increased and the pressure basically decreases. The state of gas P1, V1, T1 changes to P2, V2, and T1. As you can see over here as well, the temperature has not changed. With the absorption of heat plus Q1 for the gaseous system, the process is of isothermal expansion and is represented by isotherm AB in figure. Now this is a graph between P and V, where P is the pressure and V is the volume. So as we can see in this graph, the pressure P1 has decreased to P2, the pressure volume V1 has increased to V2, but the temperature T1 remains constant, that is same. And this line is known as isotherm, which is AB, represented in the diagram. To summarize it all, we say isotherm expansion in which P1 is greater than P2, because it was very close to over here, but it decreases. So P2 has decreased. So it is less than P1. V1 is less than V2. That means volume has increased, but the temperature has constant. That means temperature is constant. In this case, temperature is T1. Moving on with the same procedure is the adiabatic expansion. Now it has already gotten up to this point. Let us move this whole cylinder very quickly in this case, which is adiabatic expansion. The gas cylinder is now being placed on an insulating stand. That means we have placed it on material which does not give its heat or neither takes heat from it, because we know the surrounding walls of this cylinder is insulated. Then no heat enters the system or leaves the gas system. Now we know it is an adiabatic process. So as you can see, it moved very quickly in the upward direction from here till here. Here's the point. So as it moved very quickly, molecules have more space very quickly. And due to that, there's a very rapid decrease in temperature. And because of that, we can see the rapid decrease in pressure as well. So here's the diagram in the figure, as you can see, but let us read about it. Suppose the gas is allowed to expand till the volume increasing from V2 to V3, Thus, the temperature falls from T1 to T2. That means temperature has decreased because of the increase of the volume suddenly. The pressure also decreased from P2 to P3. The process of an adiabatic expansion along the adiabatic BC is shown in figure. So this is B and this is C. So as you can see, it is a very rapid process. It decreases very rapidly, and the temperature change from T1 to T2. The pressure has decreased rapidly, and the volume, as you can see, has increased in this case. Now, to summarize it in a line, adiabatic expansion in which P2 is greater than P3, V2 is less than V3, and T1 has changed now because the temperature has changed or decreased. In this case, temperature T1 has decreased from T1 to T2. Let's move on to the third procedure, isothermal compression. Now, in this case, we have to compress the piston. The gas cylinder Carnot engine is now again placed or being placed at a certain objects, which basically gives heat or basically takes away heat from its conducting base. Then placed at a low temperature reservoir at temperature T2. So let's place this piston over here. Now, because it is an isothermal process, in this process, it moves very slowly, as you can see, very gradually, and we push it down so that the molecules basically are colliding with each other, but with very minimal velocity. And because of this reason, there is a little change in temperature, but we can control that change in temperature by giving it or taking heat from it, basically putting in a core reservoir. So heat is basically absorbed in this case, so that the temperature inside this container remains constant. So it moved from here till here. That means the volume has decreased in this case. That means pressure has increased. So now the gas is allowed to expand by increasing the load on the piston. That means we increase the load, we increase the pressure on the piston. The heat energy Q2 is basically in negative. That means we are taking heat out of this conducting base and is directed by the gas, which is inside this container. The volume decreases from V3 to V4 and the pressure increases from P3 to P4 at a constant temperature. This process is represented by the reversible isotherm, which is CD, which is represented right over here. This is C and this is D. In this case, the heat is being rejected and the temperature in this case, which is T2, remains same. And we can represent this very simply as isothermal compression can be represented as P3 is less than P4. That means the temperature over here, sorry, the pressure over here is less as compared to the pressure over here. And the volume has decreased dramatically as well. The volume V3 is very big or bigger than the V4. And T2, basically, which is in blue color, remains same. That means temperature T2 over here and T2 over here remains same because it is an isothermal process and we let all the excessive heat out of this conducting base. Now for the last procedure, adiabatic compression. Now in this process, the same thing occurs but very rapidly. The gas cylinder is once again placed on an insulating stand, so there is no heat entering or leaving the system. Now we remove any conducting material which is underneath the conducting base for that, so that no heat can enter into the system or basically move out of the system. And we place the piston over here like this. So as you can see, it is a very rapid process like this. So in this case, the molecule will collide with each other very quickly. And because of that, there's a rapid increase in temperature, which will decrease the volume and increase the pressure inside the container. The gas is compressed adiabatically to its initial state. That means it goes back to its starting point, just like in the ideal case. The gas cylinder returns to its initial state, which is P1, V1, and T1 for a gaseous system. The process is represented by an adiabatic dA in the figure. This completes the cycle. Now, this whole cycle is being completed, goes back to point A. Let us represent it in summary form. So adiabatic compression can be represented as P2 is greater than P3, V2 is less than V3, and the temperature now has moved from T2 to T1. So temperature has increased in this case. Now, what have we learned? During one cycle, the Carnot heat engine performs a net amount of work done, which is delta W, which is the difference between the work done on engine during the two expansion and the two compression. The net amount of heat absorbed by the engine is basically Q1 minus Q2, where Q1 is the heat absorbed during the isothermal expansion and Q2 is the heat rejected during the isothermal compression. The area A, B, C, D, A, that means this was A, this was B, this was C, this was D, and back to A again. Enclosed by the cycle represents the net work done by the engine in one cycle. The thermal efficiency eta is given by, which is output over input. Efficiency is equal to output over input. The work done was Q1 and heat supplied basically was Q1. The work done was delta W. So we can say the work done, if we remember the first, second, you can say law of thermodynamics, that means the heat given is equal to converted into two parts. One is the heat sink and the work done. So the work done over here can be given as Q1 minus Q2. So this is the useful work done out of this whole scenario. And this is the input in our case. So Q1 is the input and W is the useful work output. So eta is equal to delta W divided by Q1. So we can represent delta W is equal to Q1 minus Q2. So now we are going to solve this equation. Eta is equal to Q1 minus Q2 over Q1. We can write down it separately. So it will be Q2 over Q1. Q1 cancel out by this one. It will be 1 minus Q2 over Q1. So this is a simplification of this eta. Here it is. Let me remove this non-equal sign. So it is equal to Q2 over Q1. We know that the absolute temperature of an ideal gas is directly proportional to the average kinetic energy of its molecule. That means as the average kinetic energy increase of the molecule, the collision between the molecule increases, so will the temperature. So they are directly proportional to each other. Q2 over Q1 is equal to T2 over T1, where T2 is the temperature of the heat sink and T1 is the given temperature in the start. The thermal efficiency of Carnot engine is also written as eta is equal to T1 minus T2 over T1, and the same procedure occurs for that as well. Eta is equal to 1 over T1 minus T2 over T1. We cancel all of this one. It will be 1 minus T2 T2 over T1. So this is the equation for temperature as well. We can use that in the numericals question. So eta is equal to 1 minus T2 over T1. So these are the two equations which we have formed from the Carnot engine. Now, what we have observed, thus the efficiency of a Carnot engine depends upon the temperature of high and low reservoir, and it's depend on the nature of the working substance. If we take the temperature of a low temperature reservoir at 0 Kelvin, then the equation will have 1 minus 0, that means temperature of the heat sink will be at 0 at absolute temperature, divided by T1, or it will be 100% because this whole thing will be equal to 0. So the output will be 100% in the case of Carnot engine. It means the work done by the Carnot engine is equal to Q1. All the heat absorbed by the heat engine is converted into work. That means Q1 is being totally converted into work done, and none of the heat is being lost in this case. Again, this is against the Kelvin statement, which said that some of the heat has to be lost in the environment. Actually, this is the real thing. That is how it happens actually. For the second law of thermodynamics, hence it is not possible to achieve the temperature of absolute zero. So we can't achieve absolute zero. That is why the Carnot engine is not possible in actual world. The efficiency of ideal engine by a theoretical limit, it is always less than 1 or 100%. So it can't be 100% because we can't get frictionless totally frictionless or total 100% efficiency machine in any case. The real heat engine cannot attain the Carnot efficiency due to the presence of friction and heat loss by the conduction and radiation. Carnot deduced from this studies that no engine could have 100% efficiency. That means there's no engine like Carnot engine. He showed that the efficiency of the best engine that could be made was functional for two temperatures at which the heat was supplied and rejected in the cycle and was independent of the nature of working substance. This statement is called Carnot theorem. No real engine operating between two heat reservoirs can be more efficient than the Carnot engine operating between the same two reservoirs. That means there's no engine like Carnot engine, which basically converts all of the heat energy into the work energy. This is not possible in real or actual world. I hope you enjoyed today's lecture. Inshallah, we'll meet again. Bye bye.